All right, let's take a look at section 2.3, and let's talk about functions. We're going to begin with a couple of definitions. So, first definition, a relation, that's what we're defining, a relation is a set of ordered pairs. And that's it. That's what a relation is. So an example of a relation might be something like 1 comma 5, 2 comma 7, 3 comma 12, 4 comma 12, and 2 comma 15. There we go. That's a set of ordered pairs. I have 1, 2, 3, 4, 5 ordered pairs. So that's a relation. Now, incidentally, these ordered pairs don't have to contain numbers. We could have anything. We could say AA, BB, CC, and DD like this. And that would also be a collection of ordered pairs. This is a relation. All right? Now, in this section, we want to consider a specific kind of relation. There's a relation with an extra condition which makes it very useful. A function. All right? A function is a relation. In other words, it's a set of ordered pairs. It's one of these things in which no distinct pairs, no distinct ordered pairs have the same first entry. And that's it. That's the definition. So, for example, this up here would not be considered a function. It is a relation, right? Because it is a collection of ordered pairs. But by definition, a function is a relation in which no two distinct ordered pairs have the same first entry. What that means is, well, these are the first entries, the 1, the 2, the 3, like that. The second entries are the 5, the 7, the 12, and so forth. To be a function, none of the ordered pairs that you have in your relation should ever have the same first entry. Here, you notice that this ordered pair and this ordered pair have the same first entry. So here, even though this is a relation, because you have two different ordered pairs that have the same first entry, that wouldn't qualify as a function. All right? This one would be a function because every ordered pair has a separate first entry. All right, so let's give a few more examples of this when we're talking about a function. Note this one right here would not be a function, whereas this one would be. Let's say we had 2 comma 3, 4 comma 7, 5 comma 9, and 12 comma 17. Would that be a function? Well, yeah, because all of my first entries are different. So yeah, this one's a function. Okay. What about something like 3, 5, 4, 7, 6, 6, and 7, 4? Okay. Would that be a function? Again, yes. Notice that you do reuse some numbers here. A 7 appears multiple times, and a 4 and a 6, but that's okay because what we're looking at is the first entry. And here all the first entries are different. So this is still a function. Okay. Now, what about 2, 7, 3, 7, 4, 7, and 5, 7? Would that be a function? Of course, yeah, that would be a function because here, yeah, the second entry repeats, but we're allowed to do that. It's okay for the second entry to have the same value multiple times as long as the first one is different. So this is still a function. Okay. Now, there is one that's slightly tricky. You got to be careful with this one. What about this one? What if I said 2, 5, 3, 7, 9, 11, and 3, 7? Would that be a function? Well, at first glance, it looks like no, that wouldn't be a function because just like this one up here, I'm reusing the same first entry. Right here, 3 appears multiple times. But this one, let's reread our definition. A function is a relation in which no two distinct ordered pairs. What's the word distinct mean? Distinct means that the ordered pairs have to be different. Here, yeah, these two ordered pairs have the same first entry, but they also have the same second entry, meaning these are not distinct ordered pairs. So it's almost as if I made a mistake and just accidentally wrote the same number twice. Okay, so yeah, I don't need to have that written down twice, so let me ignore that one. So if you don't have anything written multiple times, what's left? Is that a function? And the answer is yes. So this is still a function. So when we say a distinct set of ordered pairs, we mean if any of your points ever repeat entirely, if the first and second entry are the same, just ignore all the extra copies. That we didn't mean to write that. So yeah, that one's still a function. All right. So this gives us an idea as to what we mean by a function. Well, yeah, this is the formal definition, and yet it seems sort of lacking, because up to now we've been talking about equations and solving equations and expressions and simplifying expressions, and all of a sudden we come up with a set of ordered pairs. This is completely different from what we've been talking about. What does this have to do with equations and expressions and, well, really algebra? What does this have to do with algebra? Well, the way it's currently written, it doesn't seem like it has anything to do with it. However, a function, even though this is the definition and this is the basis of what we're talking about, there's some other properties, some other characteristics of functions that don't really appear when you look at a function this way. So even though this is the definition, we're going to look at it a few different ways. There's a few different points of view which we might look at a function. So let's take a look at a function a slightly different way. Here I have a set of ordered pairs. Let me write them down a slightly different way. I'm going to use this function right here. And I'm going to say, okay, instead of writing my first entry and then my second entry for one pair, and then my first entry and my second entry for another pair, instead of writing them as pairs, I'm going to write this a slightly different way. I'm going to take all my first entries and I'm going to write them down as a group. 2, 4, 5, and 12. Okay? I'm going to take all the second entries and write them as a separate group. 3, 7, 9, and 17. All right? Whenever you take all of the first entries of a function and write them together, that group is called the domain of a function. We'll be dealing with this word a little bit more in detail later, but for now, that's what we mean. When we say a domain, that means all the first entries of the function. When you take all of the second entries of a function, that's called the range of the function. Okay? So now, when I write it this way, you say, okay, well then, is that still a function? I mean, a function is a collection of ordered pairs. Here I don't see any pairs. I see a bunch of first entries and a bunch of second entries. Well, I'm not done drawing the function yet. Up here, there was some connection between the number 2 and the number 3. Something told us that they belong together. What's that something? We'll get to that in a little while. For now, just something told us that these belong together. So here, I'm going to draw an arrow between the 2 and the 3 that tells us, hey, these two belong together. Likewise, there's a connection between the 4 and the 7, the 5 and the 9, and the 12 and the 17. So you say, okay, so what is the function here? Is it these numbers or is it these numbers? Well, if you draw it this way, the function isn't the numbers, it's the arrows. What a function can be thought of is, yeah, it's a collection of ordered pairs. You can also think of it as a rule that says, hey, this number and this number somehow go together. This number and this number somehow go together. So when we say a function, we mean these connections between one number and another. Let's go ahead and draw another function here. Let me go ahead and use, let me use this one right here. I'm going to say 2, 3, 4, and 5. Those are all the first entries of that function. The second entries of the function, notice they're always exactly the same. It's just the number 7. Okay, and that's fine. This is the domain of that function here. And this number 7 on its own is the range. And again, I have a function which pairs this number with that number. It pairs this number with this number. The function is not the numbers, it's the relationship between the numbers. But now, let's go ahead and compare that to something that's not a function. let me go ahead and take this up here, and I'm going to go ahead and draw that one out. Now, here, I'm going to draw the first entries. I'm going to say 1, 2. Here, I don't want to make this too big. I want to keep it the same size as this one. So let me go ahead and just erase one of my points here. Let me erase one of my ordered pairs. Here, this is still not a function because, of course, the first entry and the second entry are still the same. So here, I'm going to just ignore one of them. I just don't want to have too many points. I want to have them all be pretty much the same size. So my first entries are 1, 2, and 3. That 2, I'm not going to write it again. It's already been written over here. So 1, 2, and 3. Okay. And over here, if I take all my second entries, I have 5, 7, 12, and 15. Here, I'm not going to label these as a domain and a range because a domain is all the first entries of a function. A range is all the second entries of a function. Here, this one's not a function. So if you take all of its first entries and group them together, that's just a group of numbers. It's not really called a domain because this is not really a function. Okay? So now, let me go ahead and draw the connections between this set of numbers. Okay, well now, there's something that tells us that the number 1 and the number 5 belong together. Okay, well there's a connection there. And then 2 and 7 go together. So 2 goes with 7. And then 3 goes with 12. Okay, 3 goes with 12. And then 2 goes with 15. 2 goes with 15. Just like that. So just like before, I have a collection of ordered pairs. But note that this one is not a function. Okay, well, how is this one different? How is this one different from that one? Well, let's see. If we just have this picture, and this picture, and this picture. If I ask you, looking at this picture, let's say my first entry is the number 4, and I ask you, what's the second entry? Well, there's only one right answer. There's only one second entry. If the first entry is the number 4, automatically the second entry is forced to be the number 7. Likewise here, if the first entry is the number 12, the second entry must be 17. There's no choice there. These arrows give me a relationship. Once I know what the first entry is, I automatically have to know what the second entry is. Over here, if I say, okay, my first entry is the number 3, what's the second entry? Now it's the number 7. There is no other possibility. If I say the first entry of this function is the number 5, what's the second entry? Well, again, it must be 7. Notice you don't have any choice there. There is one and only one correct answer. Look at this one. If I say the first entry of this ordered pair is 1, what's the second entry? Well, it must be 5. There's no choice there. But if I say the first entry of an ordered pair is the number 2, and I ask you, what is the second entry? You don't know. It could be 7 or it could be 15. Meaning that for every one of these, once I tell you what the first entry is, it automatically tells you what the second entry is. There's no choice. If the first entry here is 12, the second entry must be 17. There is one and only one correct answer. Here, if I tell you what the x value is, right, if I tell you what the first entry is, you have no idea what the second entry is. Right? It could be either of these. That's what we mean by a function. A function is a relationship between pairs of numbers. Now, of course, they don't have to be numbers, but for this being an algebra class, they're usually going to be numbers. A function is a collection of ordered pairs. Another way to think of it is it's a relationship between numbers that is deterministic. In other words, there are no choices. Once you know what the first entry is, it automatically tells you the second entry. If you know the first entry and still don't automatically know the second entry, that's not a function. Traditionally, whenever we have entries in an ordered pair, the first entry is called the x value. The second one is called the y value. You see that whenever you create graphs. We've seen that before. Here, once you know what your x value is, it automatically tells you what your y value is. Oh, but that's not always true. Look, if I know this x value, I still don't know what the y value is. I have some choices. That's what makes this not a function. Okay, so this gives us hopefully a clearer idea as to what we mean by a function. But that still doesn't really clarify why we're talking about these. This is an algebra class. Usually we solve equations, we graph things. What does this have to do with equations? What does this have to do with anything that we've seen in algebra? All right, well, let's go ahead and talk about these and how they can be represented. These are ordered pairs, which means we can graph them. We can put them on the xy plane. So now it starts to look a little more like algebra, right? We start to graph things. So consider a few graphs. Let's say I have this graph right here. Okay. Now, let's say that's the number 1. All right, if I have my x value is the number 1, what's the y value? Well, let's see, I can follow it up till I get to the point on the graph, and I follow it over. Oh, and that looks like that's the number 1 also, right? And over here, if I say that's the number 2, well, then I can follow it up to where the graph is, and it comes over here, and that would be, say, the number 4, or something like that, right? Notice that this x value tells me automatically what my y value is. Notice I don't have a choice there. Same thing over here. If I say x is equal to -1, well, if I follow that x value up to where it meets the graph, notice that it tells me that my y value is the number 1. And again, notice I don't have a choice in that. If x is 2, y is 4. If x is 1, y is 1. If x is -1, y is 1. I could even write these out as ordered pairs, right? I could write this as 1, 1. That's a point on my graph. 2, 4. That's a point on my graph. -1, 1. That's a point on my graph. And just like with our previous definition, I notice that my x values are all different. Compare that to a graph that looks like this. In the last section, we saw circles. So consider a circle like this. Okay? In this case, notice that if I tell you that x is equal to 0, you still don't really know what your y value is. If x is equal to 0, well, that could be this point up here, right? This point 0, 1. Oops, 0, 1. Or it could be this point down here, which would be 0, -1. Again, notice I have two different points, but they have the same first entry. So here, this is not a function, whereas this one is. The way you can tell if you have two different points that have the same first entry, remember, the first entry of an ordered pair tells you how far left or right you go on a graph. So if these have the same first entry, that means they're both an equal amount to the left or to the right from the origin. But since they're going to have a different y value, that means they're going to have a different height. The way that works out visually is if you ever have 2 points that are directly on top of each other, then those 2 points, even though they're different, they're going to have the same first entry. They're going to have the same x value. So if you have 2 points that are directly on top of each other, that graph can't be the graph of a function. Now, that doesn't mean there's anything wrong with that graph. It just means it's not going to be the graph of a function. On the other hand, if every one of your points has a unique x value, or in other words, if you never have points that are right on top of each other, if all the points are spaced out left or right, then that means that you never had a point that had the same first entry. So you do have a function. This is what's called the vertical line test for a graph. The vertical line test says if every vertical line crosses a graph no more than once. It's okay if it never crosses. It's okay if it crosses once, but it should never cross multiple times. If every vertical line crosses a graph no more than once, then that graph is the graph of a function. So consider a few graphs here. Go ahead and give this a try. There's not going to be any work to do. You just have to visually inspect this. Consider a few graphs and take a moment and think about whether or not these would be the graphs of functions. Right? So this is called a parabola. This is an ellipse. You don't have to worry about the names, but that is what these are called. Here we have what's called a cardioid. This is how math teachers send each other Valentine's Day gifts. Yeah? Here we have a cubic. Here we have an exponential. And here we have a spiral. And these are all real graphs. Take a moment and think about these. Go ahead and pause the video if you have to. And once you have determined whether or not each of these is the graph of a function, go ahead and unpause the video and we'll go through them together. Okay, so here, note that any vertical line that you can imagine crosses the graph no more than once. All right. So here, because it doesn't cross the graph more than once, then yes, this is going to be the graph of a function. Here, on the other hand, I notice that, in fact, that vertical line right there crosses the graph twice. Now, it might cross it more than twice. And in fact, there's probably other lines where it crosses multiple times. But if you can find even one, that's it. You're done. This is not a function. Okay. Here, same thing. I can find this line, which crosses the graph more than once. So again, this is not a function. This one, any vertical line that I can think of is going to cross the graph exactly once. So here, this one is a function. This is the graph of a function. Same thing for this one. Every vertical line that I can think of crosses this exponential graph exactly once. So this one is still a function. But the spiral, I notice, in fact, I have this line right here that crosses 1, 2, 3, 4 times. So that's a lot of different values, a lot of different points that have the same x value. So this one's definitely not a function. Okay, just like that. So now this starts to bring us more in line with what we normally see in an algebra class. But we can take it one step further, because these are graphs. But where do graphs usually come from? Well, graphs usually come from the solutions of an equation. If we have an equation, that equation can be solved, right, for different values of x and y. And once we take those solutions and graph them, they generate these kinds of images. So that's our connection to equations. We can think of a function as a collection of ordered pairs. All right, awesome. It's a collection of ordered pairs that has this extra rule to it. But those ordered pairs can be thought of as a graph. And those graphs come from some equation. So let's go ahead and go to that. Let's go ahead and take a look now at how equations tie into functions. So let's consider the equation 2x plus 3y is equal to 6. Okay? Now, this is an equation. Not every equation is going to generate a function. Not every equation is going to give you a collection of ordered pairs that form a function, but some do. Okay, so how do we know? Well, before we go into that, let's just go ahead and find some solutions to this. Let's remind ourselves of how that works. Basically, we're just going to plug in some numbers and see what happens. Here, let me go ahead and plug in x equals to 0. So here, if x is equal to 0, well, that's going to be, if x equals to 0, that's going to be 2 times 0 plus 3y equals to 6. course, 2 times 0 is 0, so we can just ignore that. And that's really just 3y equals to 6. Okay, but then you can divide both sides by 3, and that gives you y is equal to 2. Okay, so there's 1 point. I can do that again. If this time, let me set y equals to 0. Well, that's going to be 2 times x plus 3 times 0 equals to 6. And again, that one is just 0, so I can ignore that. So it's really just 2x equals to 6. And now I can divide both sides by 2. And that gives me x is equal to 3. So if x is equal to 3, y is equal to 0. Okay. Let me do that again. Let's say y is equal to, let's say y is equal to, let's say 4. Okay, so if y is equal to 4, that's going to be 2x plus 3 times 4 equals to 6. And that's going to give me 2x plus 12 is equal to 6. I can subtract the 12 over to the other side, so that'll give me 2x equals to negative 6. And if I divide both sides by 2, that'll give me x is equal to a negative 3. So that's a negative 3, comma 4. Notice that this equation is giving me a bunch of ordered pairs. Now, there's no guarantee that's a function, just a relation. It might be a function, maybe not. If we graph this, we get a much clearer illustration of that. Here, 0, 2, okay, 3, 0, negative 3, 4, right there. And if we start to fill in the gaps, we end up with a line. Just like that. So here, just from a visual standpoint, this does look like it would be a function. It certainly passes the vertical line test. Every vertical line you can think of crosses the graph no more than once. So this equation, when you find solutions to it, give you a set of ordered pairs. Those ordered pairs are a function. Whenever you have an equation like that, an equation whose solutions give you a function, the way you say that is that this equation generates a function. So when we say something generates a function, that means if you find solutions, those solutions form a function. Okay? Now, that seems a little long. Does that mean that every time I have an equation, I have to start finding solutions to know whether or not it's a function? Well, that is one way to do it, but that is rather long. There are certainly shorter ways to do that. Let's consider the exact same example. 2x plus 3y equals to 6. But now instead of saying, okay, let's talk about the function and see what it looks like and let's find things about it, let's be more direct. Let's ask, does this generate a function? Okay. Does this generate a function? Well, going back to what we meant by a function, and in particular this illustration down here, whenever you have a function, your y value has to be determined by your x value. Oh, once I know what x is, I automatically know what y is. That's true for all of these x's and y's. That's true for all of these x's and y's. You run into a problem whenever you have a y value and you still, you have a x value and you still don't know what your y value is. You have to have your x value uniquely determine your y value, which means that y can be written as y equals to something that involves your x, because your x has to give you exactly what y equals. So coming back over here, let's see if we can do that. Let's see if we can write y as being given by just x. In other words, let's see if we can get y by itself on one side of the equation. Here, let me subtract 2x over to the other side. That'll give me 3y is equal to 6 minus 2x. If I then divide by 3, that'll give me y equals to, 6 divided by 3 is 2, minus 2 divided by 3, that's going to be 2/3 x. Notice that what this is saying is, if I know what x is, I can take 2/3 of x, subtract that from the number 2, and I can get my y value. So that means once I know what x is, I automatically know what y is. Once you tell me x is equal to 3, I can plug it in right there. 3 times 2/3 is 2. 2 minus 2 is 0. Oh, so 3 comma 0, 3 comma 0 is a point on my graph. But more importantly, once I know what x is, I automatically learn what y is. That's what we mean by a function. Once you know what x is, it automatically tells you what y is. So whenever you have a function, if you can isolate your y as being equal to something that involves x, that tells you that x uniquely determines your y. So then that means, yes, this equation generates a function. The language that we use for this, whenever we have y equals to some equation that involves x, the way we write this is y is a function of x. That's the language for this. If y equals to something that involves x, the way you would say it is y is a function of x. These variables don't have to be x and y. You could switch them, or you could use a and b. So here the language does change sometimes depending on your variables. You can say a is a function of b, r is a function of s, or whatever variables you happen to choose for that problem. However, y and x are the most common ones. So here, because y is equal to something that is uniquely determined by x, what you say is y is a function of x. Whenever you have y as a function of x, we have a special notation for that. Whenever you have y as a function of x, you determine that because y has been isolated. At this point, we can say, well, you know what? Usually x and y are variables. You say, well, that's what they are here. Not really. X is a variable because I can choose whatever I want for x. Y isn't really a variable though, because once I know what x is, y is determined. It doesn't vary. I can't choose what it is. I can choose x, and then y automatically comes from the x. So instead of writing it as a separate variable, we're going to write it using a symbol that tells us that it's not really a variable. It's determined entirely by whatever x is. Here's the notation. Instead of calling it y, we say it's a function of x. We know y is a function of x, and a function of x is written as f of x. This x is in parentheses. That's the way you would say this. This is read as f of x. One thing to note, these are not being multiplied. When two things are written next to each other, like 2x or 3x or 4x or something like that, it usually means they're being multiplied together. But this notation, even though it looks similar, this is not a number. This f is not a number or even a variable. It's a function. It's a relationship between these two variables. So this is read as f of x equals 2 minus 2/3 x. This is called function notation. Function notation is used for a few things. First of all, it's used just as a reminder. Hey, by the way, this kind of equation fits the properties of a function. It does all of this stuff that was in the definition before. Okay, so it's a reminder that, yeah, this thing generates a function. But it's also nice computationally. It's also nice from the standpoint of notation. Here's what I mean by that. Let's say I have f of x equals to 3x minus 5. Okay, so without even checking it, the fact that I've written it as f of x should indicate to you that this is a function. Now, of course, we could check it. Right? We could graph it and check, see if it passes the vertical line test. But assuming I've written this correctly, this is an indication to everyone reading that this is a function. It sort of lets you take it for granted. It's an indication that someone else has already checked and this is a function. Now, this x represents that x. Well, what if I substituted x for something else? What if instead of writing f of x, I wrote f of 4? That's how this is read, f of 4. That x in the parentheses represents the x in your equation. If you replace that x with a 4, that means in the equation, your x is also replaced by a 4. So f of 4 is 3 times 4 minus 5. Or in other words, it's 12 minus 5. Or in other words, it's the number 7. So here, f of 4 is the number 7. What that means is that if x is 4, then because this is a function, it's automatically going to tell you what y is. Oh, and in fact, here it is. Here's your y value. So here, if f of 4 is equal to 7, that means 4 comma 7 was one of the points on your graph, or it was one of the ordered pairs of your function. Either way. Note that your function can have more than one instance of its variable. For example, I can say f of x is equal to, let's say 2x squared plus 3x plus 1. That's a function. Here I've written it in function notation, which, assuming I've done my job correctly, that automatically lets you know that it's a function. You can take that for granted. What's more is that we can simplify out this expression. In previous courses, you've been told something like, you have the expression 2x squared plus 3x plus 1. Find the value of the expression if you substitute in x equals to 5. That entire sentence can be restated as f of 5 equals, and that's it. I've just said the exact same thing. I could say, you have the expression 2x squared plus 3x plus 1. What is the value of this expression if we substitute in x equals to 5? Or I could say f of x equals 2x squared plus 3x plus 1. Find f of 5. That says exactly the same thing. Because here, by saying find f of 5, that means take this equation, and since that x value is being replaced by 5, that means these x values are being replaced by 5. Notice I have x appear multiple times. Well, that just means I'm going to plug in the number 5 multiple times. So here that's going to be, exponents go before multiplication or addition, so that's going to be 25. Next I do my multiplications. That's 50, and that's 15. And then I can add. That's 65 plus 1 is 66. So there we go. F of 5 is 66. What that means is that this function, this equation generates a function, and 5 comma 66 is one of the ordered pairs of that function. Or, if you want to think of it visually, this equation generates a collection of ordered pairs. When you graph those ordered pairs, 5 comma 66 is going to be a point on your graph. Either of those means the same thing. So go ahead and give this a try. Find f, so let me say f of x is equal to, let's go with 5x squared minus x plus 6. Go ahead and do the following. Find f of 0. Find f of 3. And this is going to seem a little strange, but see if you can do this. These are going to work exactly the way we did before. This last one, go ahead and give it a try. See what you get. I'm not going to tell you how to do it just yet. All right. Go ahead and give it a try. See if you can figure out how this works given how these work. Either way, you should be able to get these after a few minutes of trying. Do your best on this one. And whenever you come to a conclusion, go ahead and unpause your video, and then we'll go through these together. All right, so this first one is just saying, all right, anywhere there's an x, go ahead and plug in the number 0. So that's going to be 5 times 0 squared minus 0 plus 6. Okay, well, that's just going to be 5 times 0 minus 0 plus 6. Well, that's just going to be 0 minus 0, which is 0, plus your 6. Well, that's just going to give you 6. Okay, so f of 0 is equal to 6, which means 0, comma 6 is a point on the graph of this equation. Or if you prefer, you can say 0, comma 6 is one of the ordered pairs of the function this generates. They both mean the same thing. Okay? F of 3 means the same thing. We're going to go ahead and plug in the number 3. So f of 3 squared minus 3 plus 6. Okay? Following the order of operations, 3 squared is the number 9. So it's going to be 5 times 9 minus 3 plus 6. Multiplication comes before any addition or subtraction. So that's going to give us 9 times 5 is 45 minus 3 plus 6. And now we can just combine those numbers. 45 minus 3 is 42. But then if you add 6, that's going to give you 48. And there we go. So f of 3 is 48. Now, did you get this one? The way function notation works, whatever's in the parentheses, that's what's getting plugged in wherever you saw an x before. So here, f of 3 means plug in a 3 for that x and plug in a 3 for that x. Well, inside the parentheses, instead of having just a single number, I put an expression. But the way function notation works, that means that expression is going to be plugged in for x. So here, I have 5 times 3 squared minus 3 plus 6. I have 5 times 0 squared minus 0 plus 6. Whatever number's in here would be plugged in there and there. But since that's not a number, it's an expression, well, instead of plugging in a number here and here, we're going to plug in an expression here and here. So that's going to give me 5 times x plus 4 squared minus x plus 4. Just like that. Instead of replacing it with a number there and there, we're replacing with an expression there and there. Oh, but now I can simplify. Here, again, squares go first. So x plus 4 times x plus 4. That's going to be x squared plus 8x plus 16. You would have to distribute that out. X plus 4 times x plus 4. X times x times 4, 4 times x, 4 times 4. Just like that. Here we can now distribute the 5 and distribute the minus. Right? That's like saying minus 1. Multiplication comes next before any addition and subtraction. So here that's going to be 5x squared plus 40x plus 80. Distribute the 5. Now let me distribute that minus here. So it's going to be minus x and minus 4. And then I have that plus 6 on the outside. And finally, I can combine my like terms. 5x squared. Notice I have a 40x minus a 1x. That's going to be 39x. And then I have 80 minus 4 plus 6. It's going to give us 82. And there we go. So f of 3 is equal to 48. F of 0 is equal to 6. F of x plus 4 is equal to 5x squared plus 39x plus 82. One thing to note, f is a commonly used letter to name a function, but you don't have to use f. Other letters can be used as well. You can use G, H, K. Lots of letters can be used. So, for example, I could say g of x, and that's fine. That's just the name for a function. In fact, whenever you have multiple functions within the same problem, it's useful to use different letters. That way you don't confuse the two functions. If this is one problem and I'm using that function throughout the problem, okay, fine, just call it f. All right? If this is one function and I'm using it for the whole problem, fine, just call it f. But if you have 2 or 3 functions that you need to use for one problem, it would get confusing to call all of them f. So we can use other letters like G and H and K, really any letter you choose. So here I can say g of x is equal to x squared plus 5. And again, I could say find g of 2x plus 1. And again, the fact that I now have a g instead of an f doesn't change things. It's just the name of that function. It's just a label. So here, g of 2x plus 1, again, anything that's in these parentheses is what's replacing our variable. So here, in the parentheses, I have 2x plus 1. So 2x plus 1 is what's going to replace the variable. So 2x plus 1 will be squared, and then we'll add 5. Okay, so let's go ahead and square that out. 2x plus 1 times 2x plus 1 is 4x squared plus 4x plus 1. And then we have an extra plus 5 right there. Okay? Don't make the mistake of squaring each of these terms. Don't say that's 2x that's being squared and 1 that's being squared. Remember, if you're going to square a polynomial, you have to distribute it. So that would be 4x squared. That would be plus 2x. That would be plus another 2x. And that would be plus 1. And then when you combine your like terms, that'll give you 4x squared plus 4x plus 1. And then you bring down your extra 5. And now you can combine your like terms. Here, these two are just regular numbers, so they can go together. So I get 4x squared plus 4x plus 6. Just like that. All right. The last thing we're going to look at in this section is, let's go back and talk about domain and range. We saw before that whenever you have a function, a collection of ordered pairs, if you take all the first entries, all the x values, and write them together, that's called the domain of your function. If you take all the second entries, that's called the range of your function. Well, yeah, but here we don't really have collections of ordered pairs. We have equations. Now, these equations can generate a collection of ordered pairs, but notice that this would generate a lot of ordered pairs. I could plug in x is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so forth and so on forever. So that means this is going to generate an infinite number of ordered pairs. Because of that, actually trying to take the x values and the y values and write them down as a group is just not possible. You can't write down an infinite number of numbers. So how do we talk about the domain and range of something that looks like this? Well, the range of a function is actually kind of complicated. It's not something we can reliably talk about just yet. In later courses, when we talk about maximums and minimums, when we talk about other properties of functions and their graphs, we can talk more reliably about range. Domain, on the other hand, is a little simpler compared to range. So in this class, we're not really going to concern ourselves with finding the range of a function that's given this way. We're mostly going to worry about finding the domain. As long as we have the domain, that's usually enough for what we need. All right? So let's talk about how to do that. Remember, the domain of a function is all of the collection of first entries of the ordered pair. In other words, all the x values. So if you think about a graph, the x values are simply how far left and right it goes. So consider a few graphs. So let's talk about domain here. Let's take a look at this graph here. Let's say we have a function that looks like this. Sort of like a half circle. Here, this is going to be -2, and that's going to be +2. Here, we're going to say that's +1. Okay. So, if we're asking for the domain of our function, that means find all of the first entries of all the points in this graph. Oh, well, there's a lot of them, right? There's that point, and that point, and that point, and that point, all the way up and all the way down. Well, yeah, but we can describe that more simply. The domain is just all the x values starting from -2 up to +2. Okay, yeah, but all the stuff in between also. Well, yeah, but we've seen how to do that. At the end of the last section, we introduced interval notation. And an interval notation is a way of expressing not just the numbers on the ends, but also the stuff in between. Here, the domain is all the numbers starting from -2 on the left up to +2 on the right, and all the stuff in between. Okay, so that's the interval from -2 to 2. Now, do we include the number -2 as part of my domain? Well, sure, look, that point is part of my graph. Okay, so there we go, square bracket. And 2 is also part of my graph. Look, there's the point. Okay, so there's your square bracket. So from a graph, it's actually fairly simple to find the domain. You have to simply state how far left and right does the graph go. Sometimes it'll keep going in one direction or another. For example, this graph here. We'll talk about this graph later, but this is the graph of the square root function. Here, notice that it has a beginning. It starts at 0, but notice it doesn't have an end. It keeps going forever to the right. Well, yeah, but again, we saw how to do that. We've seen how to write a domain we've seen how to write an interval that goes on forever. We use the infinity symbol. So here it's going to start from 0 on the left, going to infinity on the right. Now, we want to include the 0, because look, x equals 0, that point will be on my graph. So I'll use a square bracket, but then infinity is not included. It's never included as part of an interval. You never reach infinity. Infinity just means you kept going forever and ever and ever. So here we use a round parenthesis. So from a graph, it's actually not too bad. You simply have to find how far left or right does the graph go and express it using an interval notation. Note sometimes you'll have a hole in your graph, maybe something like this. And let's say that's -1 and +1. Well, again, your graph goes from -infinity to -1. Now, I can't say it goes from -infinity to infinity because it doesn't include this piece. So I have to cut this into two parts, from -infinity to -1, and then the graph doesn't exist between here and here. Oh, but once I get to 1, then it starts to exist again. So from 1 to infinity. Notice that it's including both of those endpoints. So I'm going to put a square bracket on each of those, but it cannot include my infinities because those are not numbers. They're not part of the domain. Oop, I don't know how to spell domain. You cannot include infinity as part of the domain because infinity is not a number. Another way to think of it is if I came over here and said, okay, g of x is equal to x squared plus 5. Could you plug in the number 1? Yeah, 1 squared plus 5 is 6. Could you plug in the number 2? Sure. 2 squared plus 5, that's 4 plus 5 is 9. Could you plug in the number 0? Sure, 0 plus 5 is 0. Could you plug in infinity? I don't know how to do that. That's not a number. It's not a variable. It's not an anything. You can't plug in infinity because infinity is not a number. Or a variable for that matter. So here, the domain will not include the infinities. Everything from -infinity to -1. And then we're going to skip over this part because it's not part of the graph. And then from 1 to infinity. Because you have two separate pieces that are part of a single result, we put them together as the union of those two intervals. So there's our domain. Okay, so that's how we do it with the graph. But what if we don't have the graph? What if we just have an equation? Well, one option is, of course, you can just make the graph. But that can be time consuming. Creating a graph is not the hardest thing in the world, but it can be a very long process. It can take a while. So let's talk about how to do that with an equation so that we don't have to graph it. Let's go ahead and find the domains of the following functions. So f of x is going to equal to 5 over x minus 4. Let's say g of x is going to equal to the square root of, let's say, 2 minus x. And let's say h of x is going to equal to x squared x squared minus 9. And then up here I'll have x minus 2. Like that. All right. When we're finding the domain of a function, we're looking for values of x. We're looking for the values of x that appear on the graph of this function. Okay, but I don't want to graph it. Okay, well then let's see if we can't find values that wouldn't be graphable at all. What I mean by that is most numbers can be plugged in here. Notice if I just pick a random number, 17. Oh yeah, I can do that. Hey look, 17 minus 4, that's 13. 5 over 13, it's a fraction. It's not a nice number, but it's still a number. So here I plugged in the number 17 for x, and I got a number for y. Okay, sure, no problem. Let me pick another random number, 65. Okay, 65 minus 4 is 61. 5 over 61. Okay, so if x is 65, y is 5 over 61. Notice I'm just picking arbitrary numbers, and so what? I can pick any arbitrary number, and I can plug it in here. That's usually going to be the case. For many equations, if you just pick a random number, it's probably going to be okay. So what we want to do is we want to focus on finding those numbers that are not okay. Whenever we find a domain, we don't usually try to find all the numbers that work. That would take a very, very long time because most numbers are going to be fine when you plug them in. Instead, what we're going to do is we're going to look for the numbers that don't work. We're going to assume that the domain is every real number and then try to find the exceptions. Try to find the numbers where the results are not defined. Fortunately for us, there's not too many places that these are undefined, meaning there's not a lot of things that we don't know how to do. We know how to add most numbers, subtract, multiply, divide. We know how to do operations on just about any number. In fact, there's only two exceptions that I can think of. There's two operations that are not going to make any sense for us. Let's put it down here. The domain of a function will include all real numbers except, and we're going to have two exceptions. The domain of a function will include all real numbers except those that make a denominator 0. You're not allowed to divide by 0. So if you plug in a number that makes the bottom 0, oh, well then that's not a valid operation, which means that x value should not be plugged in. But since the domain is all the x values that can be plugged in, well then that x value isn't part of our domain. So here, the domain of a function will include all real numbers except those that make the denominator 0. And those that result in the even root of a negative number. Meaning, I don't want to have to take the square root of a negative number, or the fourth root, or the sixth root, or the eighth root. I don't want to have to take any even roots of a negative number. And you say, well, why not? We know how to do that. Those are complex numbers. We saw that in the last chapter. Well, that's true. That's not to say these are undefined. We can take the even root of a negative number. I can take the square root of negative 1. I can take the square root of negative 100. The problem is that, well, in fact, the problems, there's more than one. For right now, we're looking at functions, and we're going to be relating them very closely to their graphs. On the xy plane, I have a place to put positive x values, and I have a place to put negative x values. And I have a place to put positive y values and a place to put negative y values. If I plug in a number, if I plug in an x value, in fact, for example here, let's say I plug in the number 3. Okay, x minus 3 is negative 1, and the square root of negative 1 is I. Okay, so if x is 3, y is I. I have a place to put x equals to 3 right here. 1, 2, 3. But now y is equal to I. I don't have anywhere to put that. All right, I have a place to put positive y values, and I have a place to put negative y values. I don't have anywhere to put imaginary y values on the xy plane. So part of it is we don't want to deal with these because we're going to very closely relate functions and graphs for this course. And since there's nowhere to put imaginary numbers on the xy plane, we're going to try to avoid that. The other reason is that complex numbers and complex results of complex numbers and functions of complex variables are kind of different. There's going to be some stuff that we learn about functions which is not quite the same if you allow complex numbers. That's not to say you can't, but this being a introductory course, this is a freshman level algebra course, we don't quite want to deal with those just yet. So here the exceptions we're going to make are, you can't make the denominator 0, and that's one of those exceptions that's never going to go away. You can't divide by 0. It's undefined. This one is sort of a temporary restriction. For this course, we're not going to allow complex numbers in our functions. That's not to say they can't be. It's just we're not there yet. And that's it. These are going to be our exceptions. Toward the end of the course, we're going to have another one that joins us. We're not ready to talk about that one yet, but by the end of the course, we're going to have one more thing that we're going to be able to exclude from the domain of a function. Now, we'll talk about that when we get to chapter 4. But for now, that's all we need. Here, we're going to say, okay, let's see, my domain is every real number except for whatever makes the denominator 0 or whatever gives me an even root of a negative number. Okay, well, here I don't have any roots. There's no square root anywhere in this problem, so I don't even have to worry about that second bullet point. But I do have a denominator. Okay, so what I want to do is my domain will exclude whatever makes x minus 4 equal to 0. Oh, that's the number 4. 4 minus 4 is 0. And that's it. That's the only one. Okay, so then that means that my domain will include every real number except for the number 4. Okay, so that's my domain. My domain is, again, you can visualize the number line. Let's go ahead and do that over here. I can visualize the number line from negative infinity to infinity. I want every number except for the number 4. So that's going to be everything from negative infinity up to 4 and everything from 4 to infinity. We're going to skip the number 4, so we're going to use round parentheses, which means my domain is going to be from negative infinity to 4. And then, since we're using round parentheses, that means 4 is excluded. But then once we get to the other side of 4, 4.1, 4.2, 4.3, and so forth, then we go on to infinity. And since this is two separate intervals to form one answer, we're going to write this as the union of those two intervals. And there we go. We don't search for what makes the function work. We look for what makes the function undefined. We look for what we shouldn't have and exclude that. Whatever's left, that's our domain. Let's go ahead and look at this third one here. We'll come back to the second one. Looking at the third one, again, we want to exclude whatever gives us the even root of a negative number. Well, again, there's no square roots or fourth roots or sixth roots anywhere in this problem, so we don't worry about that one. But we do have a denominator, so we have to exclude any number that makes the denominator 0. Okay, so the domain will exclude whatever makes x squared minus 9 equal to 0. Okay, well, I can solve that. I can go ahead and add 9 over to the other side. So that's x squared plus 9. X squared equals to plus 9. And then I can take the square root of both sides. So that's plus or minus the square root of 9, which is just the number 3. You say, well, what about the numerator? Well, that's not an exception. We can have a 0 in the numerator. We just can't have it in the denominator. Right? Same thing over here. We don't care about the numerator. The numerator can be anything. It's the denominator that's not allowed to be 0. So here, the domain will exclude those two numbers, which means that everything except those two numbers is included. So imagine you have your number line from minus infinity to infinity. You have a positive 3 that has to be excluded and a negative 3. But everything else in between is fine. So your domain is going to be from negative infinity to negative 3. And then you're going to skip over negative 3. And then you want everything from negative 3 up to positive 3. And then you're going to skip over positive 3. And then you're going to want everything from 3 out to infinity. Take the union of those, and that's our domain. It's whatever is excluded with Throw those out. Everything else is our result. Okay. Let's take a look at this middle one here. We want to exclude anything that makes a denominator 0. Well, we don't have any denominators here, so don't worry about that. But we also want to exclude anything that takes the even root of a negative number. Oh, well, here we have a square root. Okay, so what we want to do is we want to exclude anything that makes the stuff inside of here negative. So we want to exclude whatever makes 2 minus x negative. Well, when we say something's negative, we mean it's less than 0, right? Positive numbers are greater than 0. Negative numbers are less than 0. Oh, okay, but we can solve that. That's an inequality. We can go ahead and subtract 2 over to the other side. All right, so that's going to be subtract 2 over to the other side. So negative x is less than negative 2. And then I can multiply both sides by a negative 1. So negative x times negative 1 is positive x. Negative 2 times negative 1 is positive 2. But since I've divided by a negative, that's going to switch my sign. That's going to be greater than. So I want to exclude x is greater than 2. So again, imagine your number line. Here's from negative infinity to positive infinity. Here's the number 2. And I want to exclude anything greater than 2. So all of this stuff gets thrown away, which means my domain is all the stuff from negative infinity up to 2. Okay, well, there we go. There's my domain. Everything from negative infinity up to 2. In this case, we can include the number 2 because notice we threw away everything that was greater than the number 2. But the number 2 itself was not thrown away. So here we can include the number 2 as part of our domain. Okay. And there we go. This is the domain of that function. For now, these are the only 2 things that you're going to toss out. These are going to be the only exclusions. In a later section, you'll see one more exclusion that's added to this list, but we'll see that in chapter 4. All right, so that brings you to your last one. Go ahead and give this a try. Take the following 2 and see what the domain is. So find the domain. Remember, you're expressing this in interval notation. Go ahead and try, let's see. Let's have f of x equals x minus 3 over x squared minus 1. Go ahead and give that one a try. And then also try g of x is going to equal to the square root of x minus 5. Let's make that a plus 5. X plus 5 over x minus 2. Go ahead and give that one a try. And then try this one. X squared plus 6x minus 5. See if you can find the domain of these 3 functions. Write them in interval notation once you're done. Go ahead and pause the video. Go through these. And whenever you are ready, go ahead and unpause the video and we'll finish them off together. All right, so let's go through these. We want to make sure we don't take the even root of a negative number. Well, we don't have any roots here, so don't worry about that. We also want to make sure we don't divide by 0. Okay, well here we do have some division, so let's worry about that. We want to exclude whatever has x squared minus 1 equal to 0. We don't worry about the numerator. The numerator can be anything. We just need to make sure that the denominator can't be 0. So let's go ahead and find what makes that 0 and exclude it. Notice here I can go ahead and add 1 to the other side. So it could be x squared equals to 1. And then I can take the square root of both sides. Now remember, when you take a square root, there's 2 values. There's a positive and a negative square root. And since the square root of 1 is 1, that's going to give me x is equal to plus or minus 1. So those are my solutions to x squared minus 1 equals to 0. So those are the only numbers that need to be excluded. You have your number line. That's everything from minus infinity to infinity. The number negative 1 and the number positive 1 are going to be thrown out, but everything else stays. So that means our domain is everything from negative infinity to negative 1, union with everything from -1 to +1, union with everything from 1 out to infinity. And there's our domain. All right, let's take a look at this one. We want to make sure that we don't have any square roots of negative numbers. Oh, here we do have a square root. Okay, so let's worry about that. So we want to exclude. Now, what you want to throw away is whatever makes the stuff underneath the square root negative, or in other words, less than 0. So we want to exclude whatever makes x plus 5 less than 0. Okay, well, that's simple enough. Just add 5 to the other side, and we're done solving that one. Subtract 5. And that's going to give us x is less than -5. Okay, so if you have your number line, you have everything from -infinity to +infinity. But you want to throw out a big part of that number line. You want to start from -5, and you want to throw out everything before that. You want to exclude whatever makes x less than -5. So all of these go away. So you're left with from -5 to infinity. But we have one more thing to worry about, because this one, not only does it have a square root, it also has a denominator. And again, denominators can't be 0. So we have one more thing that we need to exclude. We're going to exclude whatever makes x minus 2 equal to 0. Okay, well, that's not too bad. We're going to add 2 to both sides. That's going to give us x is equal to 2. Just like that. So that's the number we're going to exclude. So here the number 2 is right over here somewhere. All right, it's between -5 and infinity, so that's the number 2. So there we go. We've gone ahead and thrown away everything below -5. Notice we didn't throw away -5. That is going to be part of our answer. But we're also going to throw away the number 2. So the domain is everything from -5 up to 2. -5 up to 2. Notice we're including -5 but not 2. So square bracket and round bracket. And then we're going to take that and take the union with everything from 2 to infinity. Again, we're not including the 2, and you never can include the infinity. And that's our domain. We exclude whatever makes the radicand, the stuff underneath the radical is called the radicand. We exclude whatever makes the radicand less than 0. That's all this stuff. But we also exclude whatever makes the denominator equal to 0, which is that one number there. Whatever's left, that's your domain. Finally here, we're going to take the entire number line, but we're going to exclude whatever makes the denominator equal to 0. You don't have any denominator. Okay, so don't worry about that. We're also going to exclude whatever makes the radicand equal to a negative. Anything underneath the square root should not be negative. Well, there's no square root either. Okay, so there's only 2 things we can exclude. We can exclude whatever makes the denominator 0, or whatever makes the radicand of an even root negative. But here neither of those applies. Okay, so you don't exclude anything. And if you're not excluding anything, that means your domain is the entire number line. Remember to write the entire number line. You want everything from -infinity to infinity, so you just write that, from -infinity to infinity. There's going to be some functions where the domain is every number. They don't have any exceptions. And that's it. That's the end of our section. If you have any questions, comments, or problems, make sure you make a note of those, write those down. You can email me, you can talk to me during our next meeting. You know how to reach me. So I hope everyone studies hard and has a nice day.